One of the things that I love about the Stardust thing is just this idea that we're not just here on Earth as a separate object and place and people. Our history is intertwined with the history of our bigger space, right? That as the idea that the only reason that any of the atoms that we're made of exist is because they were made in the cores of stars, like with, burning fuel in the middle of these incredibly hot objects. And to me, that's one part of this idea that our story of how we came to be here is so intimately connected to everything else.
First of all, thank you so much for being here. As I told me in my email, you're someone who I hugely admire and look up to in so many ways. So it's a huge honor for me to be able to have a chat with you. And so obviously you, as a cosmologist, as an astrophysicist, have achieved just an extraordinary amount in your career, right? And received lots of awards. And also the kinds of questions you explore in your work, I find them just profoundly interesting, of divergence of the universe and issues like measuring the cosmic microwave background and the nature of dark matter. And I hope we'll get to some of those later in our conversation. But I always like to start my interviews by asking about people's origins, what inspired them to pursue their field. And from what I've read, for you, it wasn't like looking through telescopes or anything like that. It was more about mathematics, right? You fall in love with numbers and just doing equations. And I don't know, actually where your interest in astronomy came from. So if you could maybe tell us a bit about that.
Of course, yeah, and thanks so much for having me as well. And I will we'll get to this later, but I think one of the things that I love now is the working together with people, and that we don't do it by ourselves. We do it in these big teams, but we can perhaps talk about that later. But yeah, I didn't always know I wanted to be an astronomer. So, but I always loved maths. And so in school, that was my favorite subject. But then I realized towards the end of, high school that actually the application of maths to real problems was what that I loved doing that, because I sort of realized that actually doing physics was the application of maths to answer questions, right? That you could say, oh, how does this work? Why does this work? And that it was this beautiful combination of making sense of the world and doing it with those math tools. So then I kind of realized that that's what I wanted to go and study at university, was probably physics. And then once I was there, I even then didn't think I wanted to sort of be a researcher. But the thing that grabbed my attention was just a really cool, reality of the universe. I did it in my first year at university. We did a special relativity course, which was the first time I discovered that again, time and space are not absolute. Things kind of change. And we had a fantastic lecturer who just was very inspirational about sharing the excitement. So I think that was probably when I first got to think, oh, maybe actually, astrophysics and the universe were the kind of questions I liked doing the best. But it really took until then, even later, kind of having done a research project at the end of college and then actually leaving university thinking that I didn't want to be a scientist, to then realize that I missed thinking in the way that I do now. So I then did do a PhD, but it took me. I sort of left university and then realized that I missed that way of thinking, and then came back to do a PhD.
And, I'm not a scientist myself, as you know, right? As I, told me in my email, but I absolutely love science and, find it fascinating. I've been doing more of science journalism, recently, talking to people like you. But, for me, that interest in science, even though I'm not a scientist myself, it all began with, I guess Stephen Hawking. I remember when I was, very young, I was reading a lot of his paper science books, about the universe, and also learning a lot about his life story, because he's been obviously a huge source of inspiration to millions around the world. And I was just curious, since you studied at Cambridge, where he was a professor, right, for decades, maybe did you have the chance to meet him while maybe starting or later after you graduated? And if so, what was that like, if you can?
Well, I will say, so I never sort of interacted with Stephen Hawking in terms of, discussing work or anything, but I will say that he 2 times came to a seminar that I gave in Cambridge. And I remember being quite intimidated by this experience, to give a seminar about your research and have Stephen Hawking there I found that kind of again a little intimidating, but it was wonderful, that he was there. That's really been the limit of my interaction. He was so well obviously respected around the Cambridge. That was when in Cambridge. Yeah, no, he's of course a huge figure in the history and importance of our field.
Maybe. Do you have a scientific hero of your own? It could be someone still alive, or someone from history whose life you find especially inspiring. Maybe.
Yeah, absolutely. Well, I mean, there are a few in different ways. For me, particularly, there are a number of the kind of leading women in our field who just did amazing things. There was Vera Rubin, who is one of my big heroes, and I'm so delighted that now one of our most important observatories is named after her. And again, we could talk more about her, but just the level of kind of pushing forward to understand what you want to do while juggling family and life and also battling at the time against presumptions of whether women could do science or not, or how well makes her one of my heroes. Also Jocelyn Bell Burnell, who had this enormous impact on discovery of pulsars, but is also just a fantastic person, and has been inspiration to me. And then there were some earlier characters like Henrietta Swan Leavitt, who did really important things in astronomy. And it's not only them, but then in other ways, there are other people who've really inspired me. Like, again, you mentioned, reading Stephen Hawking's work. One of the things I did after leaving university was reading Brian Greene's book, The Elegant Universe, and that his ability to kind of just excite, me and others with these topics. I love that. So anyway, those are some people.
I have this lovely image. I hope you'll be able to see the pale dot image. Yeah. So,
yes, very good, very good.
Yeah.
No, he's an amazing person.
Yeah. And I sometimes bring up this image because I, for me, when I first saw it, and obviously I read a second, beautiful description of it. He was talking about how everyone that you've ever known, right, has lived on that, tiny dot. That kind of gave me a completely different perspective on things. I was curious, have you had maybe a similar transformative experience like that? I bet you as an astronomer, you must have gone to some pretty amazing dark skies, right, on the planets, and maybe and you got to see the Milky Way in its majesty, and maybe it kind of changed your perspective on things.
I have a particular recollection where those two things were a little bit combined. That, again, having left university, not knowing what I wanted to do with my life, my career, anything, I actually backpacked across South America, from Ecuador to Brazil. And in a span of a couple of weeks, I actually was reading The Elegant Universe by Brian Greene in Peru and Bolivia. And then I went on this incredible, tour of the salt plains in Bolivia, which turns out to have been incredibly close to now where the telescopes I use in Chile are. Just so the coincidence was kind of remarkable. And the skies there, which is in the Atacama Desert, one of the clearest, driest places on Earth, and again, now where the telescopes I use now are, the skies were incredible. It was so dark. And that was probably my first experience really seeing skies like that. I grew up in London, of course I'd been to darker places, but my real experience of the night sky was not like that. And I do remember just being in awe of the number of stars and seeing the Milky Way. And it was actually at a time where I was also reading about the sort of fundamental physics, about string theory and the fundamental, ingredients of the universe. And I did love that. And I do remember being quite sort of influenced by both the kind of cool physics and also just the beauty of the skies. And I do think that's what I love about astronomy, is it combines real just aesthetic beauty with kind of mathematical beauty as well.
Since I mentioned Carl Sagan, for those who haven't heard of him, for some reason, he was, of course, he was a great scientist and just a wonderful, science communicator. And he wrote some fabulous, books about the universe, and also did this TV series Cosmos that you maybe you might have seen as a child, right? Or I remember he talked about how we're all made of star stuff, right? And I've always found that idea so like beautiful and profound. And I know that you, for example, in your own book, Our Universe, right? You also have a chapter, like literally called "We're Made of Stars," where you also explore this idea. And to me, it's just such a beautiful fact that we know about the universe. I was wondering if there is maybe one fact like this that is just so like mind-blowing to you, and maybe what do you find most beautiful or most amazing about this whole thing? Maybe you should.
Oh goodness, yeah, there's so much beauty about. I think that as you said, one of the things that I love about the Stardust thing is just this idea that we are all part of. We're not just here on Earth as a separate object and place and people, that we're intertwined. Our history is intertwined with the history of our bigger space, right? That as the idea that the only reason that any of the atoms that we're made of exist is because they were made in the cores of stars, like with burning fuel in the middle of these incredibly hot objects. And to me, that's one part of this idea that our story of how we came to be here is so intimately connected to everything else in the universe that we have to understand. I work on the Big Bang and the kind of the sort of big story of how we started and how we came to be there, but it is our story. It's not. I don't feel like it's. I think sometimes there's a perception that that's like something else out there. It's not us, but we are part of it. That if we want to know why there is a planet here, it's because we formed around a star, and the star is there because a long time ago a galaxy formed, and then I go back even further and say, well, where did the galaxy come from? Where did that start from? And I go back and I look at the very earliest moments in time before there were any galaxies, and I look at the tiny sort of ripples, features in actually the very, very earliest moments of the universe, where we just see little lumps of hydrogen and helium. And that's what I spend a lot of my time doing, is looking at these kind of like this very early image of the universe. And the fact that I know that we sort of we started there is, to me, just really amazing, that we can sort of trace our history back 13 billion years.
What's maybe one big question that you would love most to see solved in your lifetime?
I maybe will give you two, but the first one is dark matter. So yeah, there is this weird situation right now, and it's been around now for years, that we know that this large amount of the universe is completely invisible, right? There seems to be mass of stuff, then we call it dark matter, that's 5 times more plentiful than the atoms that we know of, that we're made of. And again, it sort of follows the laws of gravity, but it doesn't seem to emit any light, and it doesn't interact with stuff. There's probably dark matter, flowing through me right now. It doesn't interact with my body. It doesn't interact with your body. And we've known about it for nearly 100 years, and we've been really sure of it for, maybe 50 years. And it continues to be this mystery and about what it is. Is it a new particle that we just, again, can't see because light that we use to look at things doesn't interact with it? And I really hope we have found out something about it, during my lifetime. There is a possibility that we won't, because it may be that this stuff is so non-interacting that we just won't know. I hope that's not the case. So yeah, if we could figure that out, because also there's a connected thing, which is that until we figured it out, we also sort of have to worry, have we got something really big wrong about our understanding of, the laws of physics or the way in which the universe works? That until we've sort of understood it, I feel like it's too big a missing piece of the cosmic puzzle So that's one of my things. I also would like to know how fast what was happening in the universe in the first fraction of a second of time. That's a very separate thing, but it's also the thing that that really excites me.
You were awarded the Breakthrough Prize for Physics, right? In some years ago, and you shared that with other members of the so-called WMAP science team. If you could describe for us like what it stands for, WMAP, and what that project was all about.
Yeah, absolutely. So yeah, I was very lucky so when I finished my PhD, I did a thing called a postdoc, which is what we usually do after that, a research job in Princeton. And I got to join this team of scientists working on WMAP. So WMAP stands for Wilkinson Microwave Anisotropy Probe. It's a bit of a mouthful. But what it was, and the Wilkinson was named after David Wilkinson, who was a key member of this team. But who sadly died before it was all finished. What was this? It was a satellite launched by NASA, and its goal was to make a better image of the earliest and oldest thing that we get to look at. So this is what I've then spent most of my career doing, which is studying this thing called the cosmic microwave background. And I find it magical that we can even see it, and we can't see it with our eyes, but we can see it with our telescopes, with these probes. It's the furthest back in time that we can look. So in astronomy, we're always looking back in time by looking out in space, because light takes time to reach our eyes. And so the further you can see or measure, the further back in time you get to look. And this cosmic microwave background, again, then the microwave is because the light that reaches us now is stretched to microwave wavelength. It's typically kind of a millimeter or so in wavelength of the light. It carries this image of what the universe looked like when it was only a bit less than 500,000 years old. It's not an image of the whole universe. It's just an image of a part of the universe. It's kind of like, imagine it's a sort of a sphere around us, the surface of a sphere around us. We just get to see what that bit of the universe looked like just after its birth. What does it look like? It's, again, if you step back to that time, at that point there were no galaxies and stars and planets when the universe was only, again, almost 500,000 years old. And all there was kind of a sea of hydrogen and helium atoms. And this image shows us sort of where they were and how they were behaving. And WMAP, the satellite, basically revealed this image in much greater detail than had been ever seen before. The previous image came from the COBE satellite. And, why is that interesting? Well, it's interesting for two reasons. One is because you can imagine then, if you see this image, you can then again, as I mentioned before, it actually shows you the kind of seeds of cosmic structures. These little kind of, you see these like lumps and bumps in it. People may have seen it. It's this kind of iconic kind of red and blue blobby image. And those blobs really are just the kind of initial tiny features in the universe that would later grow to make galaxies. But we can also use it to kind of wind time backwards and say, well, why are they there at all? Why are we here at all? It's because there were some those initial kind of features that could form us later, and we can look at it and try and understand where they came from. Like if you then go back to sort of time zero, to the Big Bang itself, how were they put in? So anyway, I could say more, but the WMAP basically made an improved image of that. And one of my jobs on the team was to use it to kind of try and extract numbers like how fast is the universe growing, what were the ingredients of the universe, how much dark matter there was, how much regular matter, how old is the universe. So that was my job in that team.
Okay, I want to again show this lovely book of yours, and for me it was a fantastic introduction to astronomy, and it inspired me to learn more about some of the things that we've been talking about already here. And I was curious if you were writing an updated version of this book, today, if there are any major, discoveries or observations that you would want to include from, say, the past. I guess it was published in 2019, right? From the past 7 or so years, right? Maybe if there are some really big discoveries that you would like to include. When scientists took that famous first ever image of a black hole. I guess it's not included in the book. Yeah, maybe it's one of the...
No, exactly. I mean, what I find amazing about what we do is that exactly books like this will be out of date instantly because we learn new things like all the time. Every week, every year, we learn new things. So exactly, a few of the major results in recent years have been exactly the fact that we can actually we can see this image of stuff around a black hole and see the black hole in the center of a galaxy. There's also been enormous progress. I did mention in my book the first discoveries of gravitational waves from inspiraling black holes and from and their effect, but that field has really moved on a lot. There's now like regular huge numbers of detections of black hole mergers that are seen by the LIGO experiment that were just kind of starting at that point, and now it's become really a much bigger field. And then I think one of the major things that's happened is also the launch of the James Webb Space Telescope. That finally launched successfully, and has just been revealing so much amazing new science from both. Again, it can do so much as it's got very high resolution, which means it can see in great detail. And so for objects that are closer to us, like in our galaxy, it's just given us beautiful images. I'm sure many of us have seen them of again, star forming regions, the birth where stars are born. Just to be able to see them, to see this so well has been amazing. But it's also been revealing kind of very early galaxies that it can see it. I was saying what I look at is this image of light that comes from before galaxies formed. And the James Webb Space Telescope is now able to sort of look at those first galaxies just a little bit later, but very early on in the universe's history. And some of what they're finding is unexpected, unsurprisingly, that lots of very early galaxies have been found. And a number of them are not yet fully understood. And, there are lots of now interesting questions about, again, how the very first galaxies formed, how many of them there were, do they make sense, in the context of what we think the physics was? And so there are all these new questions and as well data that are being gathered. So I think a lot of the field of astronomy is now quite driven by the JWST data.
You spent a lot of time, describing fascinating history in your book, Our Universe and Astronomer's Guide, right? How we came to accept, the Big Bang theory itself. What I find also interesting is that I guess people in your field, cosmologists, astrophysicists, you have a lot of respect and reverence perhaps for Einstein, given his immense contributions to the field and the kind of impact he's had on our understanding of the universe. But what's also interesting to me is that while he was obviously like a revolutionary thinker, in many ways, and probably should have won several Nobel Prizes, not just one, for his discoveries. But he was also famously resistant to some ideas, right? Many of them that came out of his own theory, like the idea of an expanded universe, black holes, and the Big Bang itself. It's just a fascinating mix. Like someone like we sometimes have this picture of him as this like genius who got everything right, but it's not quite true. He was also some of his intuitions turned out not to be correct. When applied to the whole universe, let's say. And for me, just the story of how we came to accept the Big Bang theory itself is just so fascinating. And maybe if you could walk us a bit through that history, and maybe because start with Einstein and maybe move all the way to like the 1960s. I guess that's when pretty much everyone became really convinced that the Big Bang really happened. When scientists by accident observed that CMB light. Maybe if you can take us a bit through the history of that, if that's not asking too much.
Of course, no, I'd love to. I can certainly say something about that. So, yeah, because I think it's true that we all have this great. Well, I think most of us have this enormous respect for Einstein's discoveries, because the fact that he has this beautiful equation, right, that basically says how things in the universe follow the path of a deformed space, and this connection of how objects in space relate to the deformation of space itself, and then that tells us how things move. It's just incredible that such simple and beautiful equations can describe the entire, behavior of the entire universe. But indeed, he developed this theory of general relativity. But at that time, in the early 20th century, he didn't think that the universe was a changing place. So at that time, the idea was maybe that the whole universe was just our galaxy. And what we know now is that our galaxy itself is not expanding. And of course, it's changing, but it as an object is not really growing. And so people hadn't made the measurements that maybe we lived in an expanding space with galaxies beyond our own. But there were, a couple of key scientists sort of took Einstein's equations and said, well, if I try and solve them for a kind of universe-like space, the solutions to it would say that either the universe as a whole or a space itself should be growing or shrinking. It should either be expanding or shrinking. It shouldn't be staying constant. And one of them was Georges Lemaître, who was a Belgian scientist. He was also a priest and a scientist. And then also Alexander Friedmann wrote these equations down and basically sent their work to Einstein to say, look, these are the natural solutions of your equations for the universe as a whole. Einstein hated these. He didn't think that he said that these are kind of solutions to the equations, but this isn't how the universe works. He just didn't think that was true. And actually, it took more observations by a number of scientists and then kind of really promoted most by Edwin Hubble, even though Georges Lemaître actually did a lot of this too, that basically showed that there were galaxies out beyond our own and that they were moving away from us or appeared to move away from us, which is exactly what you'd expect if space is growing. If we imagine space scattered with galaxies, each galaxy is kind of 100 billion stars gathered that gravity pulls together, that these galaxies, if space itself is growing, they should all be moving apart from each other. And this was then seen with the data. And Einstein then did come around to it. Like he was convinced by these observations that, this is that there are galaxies beyond our own. We are expanding. The universe is changing. And so he was convinced, but I think my understanding is, it took a while for that to happen. And then that observation that, again, that galaxies around us are moving away from us and the universe is growing, one obvious consequence of that would be that it all began in a Big Bang. And this was then one of the prevailing theories or ideas about what this all meant, was that, okay, if everything is moving apart from everything else, and if we wind time backwards, then sometime in the past, everything should have been back on top of everything else. Space should have shrunk down to kind of a singularity or 0 point. And so that was the idea, that maybe there was a Big Bang.
It would be lovely if you could talk a bit about that. Very important figure in that whole, in the development of the Big Bang theory, I guess, is someone called Georges Gamow, right? He was, and what I love is that he was actually born in Ukraine. He was born in Odessa. Yeah. So I love that Ukraine has this has some place in that story.
Yeah, no, he's an enormously important figure in our field. That's right, Georges Gamow. So exactly. I'm delighted to hear that. So exactly. So around. Soon after, right, these observations were made about, maybe the universe is growing and maybe there was a Big Bang. Exactly. Gamow and others were working through the theory of, like, if this had happened, what else should we expect? And indeed, they came up with this idea that there should be this background, this sort of bath of light coming from that emerged at the Big Bang. And again, the idea of that is that if we do imagine the universe back in reverse, we kind of shrink everything back down so that it's more closer and closer together. The temperature of the universe should go up and up and up as we go back in time. So what we think was going on at the very then, and if we imagine what was there at the beginning, we imagine, let's say galaxies had not formed, stars had not formed yet, but we imagine that there were atoms. And again, these theories suggested that the only things that would have had time to form in such a universe were hydrogen and helium. So if we imagine the universe sort of cooling and expanding, that And this is this idea of why we're all made in stars and not in the Big Bang. So if we go back to that early time, the theory showed that we should only have hydrogen and helium at that point, a little bit of lithium, but almost nothing else. All the carbon and nitrogen and oxygen that we're made of just hadn't formed yet. And that was the stuff that was made later in stars. Okay, so hydrogen and helium. And then also light. So the expectation would have been that the early universe would have just been this hot state of hydrogen, helium, and the light. Now we also put in dark matter to the mix as well. So we think there's also some dark matter, but let's ignore that for now. Okay, and if that's what you had, when the universe was very hot, then the hydrogen and helium atoms would be so hot that they would be broken apart into their protons and electrons. That's if you sort of give a lot of energy to an atom, it breaks it apart. And so what we talk about is, and again, the theoretical ideas showed, was that the universe should then be this hot kind of plasma early on. But there were this critical moments, again, this is just less than 500,000 years, when the universe would cool down enough such that this very important thing happened, which was that atoms could now, instead of being broken up, they could actually form into whole neutral atoms of hydrogen and helium. And the prediction then is that rays of light that previously would have actually scattered off the electrons that would be around in this plasma, rays of light don't really scatter off hydrogen and helium atoms, and they could then travel through space. And then the idea is that those rays of light would have traveled through space just forevermore until they reach us now. And this is this bath of light that we now call the cosmic microwave background. That was predicted to exist. But yeah, indeed, the theory was sort of developed, and so again, this would be sort of be the second critical evidence for the Big Bang, because then not only would we see the galaxies all moving apart from us, but if we see this light, this bath of light around us, and it should come from every direction in the sky, then that would have been generated just after the Big Bang. So yeah, but the prediction was made before it was seen, because the signal is tiny. It is this light now. Its effective sort of temperature is minus 270 degrees. It's 3 Kelvin. It's incredibly faint. And you can't see it with your eyes or even regular telescopes. You have to have a dedicated telescope that can measure this as sort of microwave light. And that was done in the 1960s. And again, it was done in this wonderful, I now work in Princeton. There was a team in Princeton who were actually looking for this light. Jim Peebles, who's still there, was one of who actually re-derived a lot of the theory that had already been worked through, but he sort of derived it separately. He and then Bob Dickey were looking for this light on the roof of a building in Princeton that's now opposite the road from where I now work. They were looking for it, but then two scientists actually just an hour away in New Jersey, working at Bell Labs, detected this light by mistake. They thought it was just kind of noise in their instruments. But they realized through communicating via, again, Jim Peebles, who presented some of this work, they were like, oh, this is important. So they contacted the Princeton colleagues who said, actually, you found the light from the Big Bang. So this was Arno Penzias and Robert Wilson who did this. Yeah.
There was this famous quote, like, we've been scooped or something like this. Yeah.
Yeah, exactly. And it really, Jim was in the room. He said that this is, he confirms this is what was said. So they were having a research meeting in Bob Dickey's office, and Bob Dickey got a phone call from exactly these scientists. And after speaking to them, I think he exactly turned to the group and said, well, boys, we've been scooped. But it was the start of something amazing, right? Because so soon after that, then the Princeton group did in fact detect this light from the roof of the building in Princeton. And that just set off this whole field of research that, we're still working on now. First of all, it was just about detecting the light itself, like it was just finding it. And now it's about kind of mapping out the details of it, and actually taking advantage of the fact that it's not completely smooth, and that we can use the features in it to actually learn about our universe.
I remember I also was talking to, I'm sure Kip Thorne. He won the Nobel Prize actually for
Yes.
the observation of the gravitational waves, right? And he was like one of the co-founders of the LIGO project. And I remember I asked him about whether he feels optimistic that we might be able to see these primordial gravitational waves, right? Coming from the Big Bang itself in his lifetime. And he said yes. So. And he's like 85 now, so he's quite optimistic in that regard. Maybe I know about you, how you feel.
Yeah, well, I mean, that's actually what really my group are primarily working on right now, is our search for that primordial gravitational wave signature. Yeah, so there's this wonderful, and actually I remember a number of years ago, before LIGO actually detected this signal from black holes, I remember having we would discuss, with amongst the community, who's going to see gravitational waves first, right? Is it going to be LIGO with the black holes, or is it going to be that we see them via their cosmological imprint? Now, LIGO obviously won that contest, but now we're trying to see the early ones. So yeah, the idea is that if we think that the universe underwent this accelerated expansion right at the beginning, and that put in, it's really cool actually, that like the quantum fluctuations of just like sort of empty space, almost empty space-time, created the features that then have now grown into us. Like, that's amazing. Okay, but the prediction is that if this accelerated expansion happened, and that indeed quantum fluctuations were happening in that space, they should have imprinted these specific kind of irregularities in space, which we talk about, we call tensor perturbations or tensor fluctuations, whatever. They're sort of like they're irregularities in space that aren't sort of symmetric. They're like, you can imagine an irregularity in space with just like a lump, right? That's like the gravity kind of pulls stuff into. But you can also imagine irregularities that are sort of stretched in one way and squeezed in another way. They're a different type of feature that could have been put in the early universe. The critical thing about these is if they were there, then they would have been put in at the beginning, and then what they would have done is travel through space as gravitational waves. And again, a gravitational wave is space itself sort of stretching and squeezing in one direction, and then stretching and squeezing in the other direction, and back and forth as it sort of propagates, as it travels through space to you, for example. Okay, and if they were there, now they would have by now, if they were put in at the beginning, they would be long, they would have just, died down by now, but they would have left this critical imprint in how light was polarized back when at this image that I look at, so the image that we capture of the universe, the CMB, the cosmic microwave background, it would have left this it would have polarized the light in a particular way, again, because of the squeeze. If space itself was sort of squeezed, then it would give this particular kind of orientation of the light. So what we're doing now is trying to look for this imprint of polarization in the CMB. And I'm so excited right now because we have these new telescopes in Chile that are dedicated to looking for this signal, and they're working now, and they have been on the sky now for the last, year or two. And they are right now kind of scanning the sky in Chile with incredible sensitivity, looking exactly for this signal. And the team of, postdocs and students that I and many other people in our team are working with are really digging into the data and trying to find this signal. It's early days, but I think I hope for Kip Thorne, it's depending on how big the signal is, then sure, in 5 or 10 years, if it's big enough, we could see it.
Yeah, but I also love the idea that we could learn so much from this, primordial gravitational waves, right? If we were ever to detect them, and especially things like I've heard scientists say that we might be able to figure out whether we live in a multiverse.
In fact, I'm here in Philadelphia right now because we were having a meeting to celebrate. Actually, Wendy Friedman, who's a well-known astronomer, receiving a prize, Franklin Award, for her work measuring the expansion rate of the universe. And so I was speaking yesterday about this thing that you can both use the CMB, the cosmic microwave background, to kind of measure the expansion rate of the universe today, But the thing we really would also like to do is measure the expansion rate right at the beginning. That's the thing that reveal. If we can measure these gravitational waves, we would know how fast the universe was growing in the first fraction of a second. And that would tell us the strength at which it was being pushed apart, and would tell us something about what was pushing it apart. Because what we would really like to find out is, why did that growth start? What was pushing it? And indeed, if we could then learn more about that, we might be able to learn more about whether, different parts of the universe maybe started expanding at different times, how they grew. It's exciting.
So maybe besides the search for those gravitational waves, if there are any other big projects research projects that you would like to pursue in the future, maybe if you could share it with us.
Of course, there's one thing that I really hope that we'll do too, that actually the landscape of it is changing again as we, year by year. So there's a really neat thing that we can do with cosmology, which is actually measure how much neutrino particles weigh. So neutrinos are the tiniest particle that the least massive particle we know of. And actually, until somewhat recently, people thought they didn't have any mass at all. And now that we know that they do have mass, and again, they are actually a kind of dark matter. They're the sort of dark matter that we do know about, in the sense that they don't interact with us. But they do very, very weakly. They do very, very weakly interact. So they're not completely. They are interacting, but very weakly. Anyway, so cosmologically, they sort of behave like dark matter. And right now, there are billions of them flowing through, our hands or bodies at the moment. But they're quite mysterious particles. We don't fully understand why they have mass, really much about them. But there are enormous numbers of them in the universe. And what's really cool is that even though you can try and measure their mass with laboratory experiments here on Earth, we can also try and measure their mass using their influence on how cosmic structures have formed. Very broadly, they are, they're such tiny particles that when the universe was much hotter, they would have been just traveling basically at the speed of light. That it's only their tiny mass that stops them from going completely at the speed of light. But when the universe was much hotter earlier on, they would have just been traveling this really fast. And so the more kind of massive they are, the more of the dark matter they do make up. That's the big question we have. How much the dark matter is these neutrinos? And they actually would have changed how big cosmic structures look. They kind of smooth out the features of giant cosmic structures. So what we can do is try and weigh them by looking at how much mass, looking at their effects basically on large cosmic structures. And so we're trying to do that using the CMB now actually as a backlight. We actually measure how much it's been kind of gravitationally distorted by all the stuff in between. So instead of thinking it as the image itself, we're now thinking also of using it as we're looking at how much the light rays that travel to us have actually been gravitationally bent by matter on the way. And so we're using that as a way to try and detect how much these neutrinos weigh. So I love the fact that you can use the entire universe kind of as a laboratory to sort of measure something, a fundamental physics thing like that. And then they're connected to all that. We haven't mentioned it, but it is ongoing in our field and is particularly relevant right now, which is, I didn't even talk about dark energy, right? Which is this idea that the universe seems to be accelerating again, right? And that the sort of best idea is that maybe empty space itself has an energy. This is what we call the vacuum energy, or lambda. But there are some hints right now from observations that maybe it's changing with time, that maybe it's a new thing that we haven't yet fully understood. So some of our observations and some of the interest I have in our field is sort of to see where this goes. What can we understand what this other mysterious component is? So we have the dark matter, but we also have this thing called dark energy. So that's the other thing I hope we'll make progress on.
And lots of people talk about now how AI is going to revolutionize everything, right? I guess AI is already playing an increasingly large role, right, in scientific research and maybe even contributing to new discoveries. And I'm just curious now, you probably use it on a regular basis in your work, and maybe how do you use it, and in what ways do you find it useful?
Yeah, no, I can say, I mean, I find it already a very useful tool. So it's amazing, especially because what we do, a lot of what I do and what we do is computer coding, right? Where we're taking data and we're matching it up to theories, and the basis of that is computer code. And AI can write that computer code much faster than we can. So it's definitely very useful already for like speeding up bits of what we do. At the moment, I see it as, a useful tool that we're still understanding how to best use, because the really tricky part of it, and there's been lots of discussion about this, is that it can generate code and results very quickly, but checking whether they're right is the really hard bit. And of course, when we do science, our big job is to check that we're right. So I think that's the thing that we're all grappling with, is how to best use it as a speeding up tool, but also how to trust it. And so it's a huge challenge, and also how to make sure that they're not losing the training of our younger scientists, because it's no good if I just having had having received all this fantastic training in how to be a scientist, I could then take those tools and speed up what I do. But if I don't then train the next generation of scientists to do science with the tools that exist at the time, then science stops, right? Science only works because we have generations and we pass on the baton, right? We show the next generation of scientists how to do science. So I think the thing that we have to address is just how to keep training the next generation, so that it doesn't all just stop. But how to use the tools in a good way. It would be ridiculous to think that we were just not going to use those tools, right? They're too useful, they're too good. But we must figure out how to do it in a way that works and that we're still learning. Because I think the point of doing, again, many people have said this already, we do science to learn about our wider world, of course, in many ways to have important applications. But I think in astronomy and fundamental physics, a lot of it is the learning to kind of enrich our lives as humans. And so if we then stopped learning and just had the AI do it, then we also haven't really done, why are we bothering? So yeah, I think we're all grappling. It's interesting times. We're in a revolution, and it's going to be just very interesting to see how the doing of science evolves. Yeah.
As a Ukrainian, I'd be curious to hear, if maybe you have some message for us Ukrainians on how to navigate these difficult times.
I mean, maybe I can just say that I have such respect for those of you in Ukraine who are dealing with this, living through this. That obviously that life is harder and more challenging than those of us who are living in a peaceful place where we're not having to grapple with this. So I have such respect and admiration for all of you doing this. And I hope, and I think you've expressed this too, that I see what we do in astronomy and cosmology as hopefully just providing a bit of enrichment of our lives in the same way that art perhaps does, maybe music or other things can just make challenging lives a bit more. Give the positive and give the reminder of what we as humans can do together, and that thing of a science being a human collaborative endeavor. I hope that is a more important collaboration than conflict.
I often like to end with this kind of philosophical question. When you, for example, reflect on your life and many amazing contributions that you've made, in your career, what would you say, gives you the greatest sense of purpose and meaning? What life means to you as a scientist or as a human being? Or maybe maybe it's not even about the science itself for you. Maybe there's sort of more to it than just science.
I can actually say, I mean, it's connected a bit to my scientific life and my home life, that actually training junior scientists has been probably the most rewarding thing, and seeing them learn and then go and succeed and build careers. I think that's the most fulfilling part of what I do. And then I would say that jumps over to, my home life where, I'm a mom and I have kids, and seeing them kind of learn and grow and make their way is also, to me, deeply satisfying. So to me, those two are but connected and important.
Maybe also like seeing your work being recognized and people, using it in their like own research.
Seeing them succeed and do more research. And because the thing is that I won't be around forever. And so to see science succeed and continue, they have to do it. And so, you're passing it on. We do a bit and you pass it on, and then you...
Thank you very much for your time. I fully understand how busy you are, but I'm very happy that you found some time to chat with me. And it's very much appreciated. You're one of my heroes, so when I get to talk to one of my heroes, it means a lot to me. So yeah, maybe there's some final thoughts you can share before we wrap up.
No, I really appreciate it. We're all doing, I get to do what I do because of all the people who I've worked with who've supported me. And so, and I appreciate you also sharing the science and the excitement with others, because the learning and the sharing together is what makes gives it any point, I think. So I'm grateful to you too for, getting out these things.